Now we start the section 3.2, derivatives of polynomial, exponential functions, and trigonometric functions, and the product rule. So, you asked me to see the proof of the product rule. So that is going to be our objective of today's lecture. Yeah, you know the derivative of constant is 0, and now the power rule says if n is a positive integer, then the derivative of x to the n is n times x to the n minus 1. That's what you are using. It works for the polynomials. Okay? So the proof. Let's see the proof of this power rule first. Let f of x is x to the n. Then using the formula x to the n minus a n is equal to the factor out by x minus a, then you know this from the factoring in수분해. You must know all this. So we just use this simple fact. F from a can be written in this way from the definition, which should be written in this way. Then use this equation to rewrite it, because this x minus a and this x minus n can be cancelled out. So what's left is this. When x goes to a, then each of terms makes a to the n minus 1. So how many of them are there? That's n minus 1 terms. So we have n terms. So we have n times a to the n minus 1 here, which gives us this power rule. Okay? So you must have learned this during the high school years. This proof from the definition. Okay. Now, general power rule. If a is any non-zero real number, then it still works. That power rule works not only for the positive integer. It works for any non-zero real numbers. Still, the proofs are similar. That the first part makes one part, and for the negative part, you have to prove separately, and you have to expand it to the other real numbers, the rational numbers. So there are steps to prove it in a general form. So many mathematicians have worked on to generalize the power rule up to this in the similar way that you have seen. Find f prime of x when x is equal to 1 over n. It's a rational case. The proof. Note, we may think first f of x might not be differentiable at x is equal to 0. Okay, when n is not equal to minus 1. So find the derivative of this for the rational number, not the integer number. Here we had the for whole real numbers. Now we have an example of a special case of the earlier theorem. So in here, the proofs are quite simple. Let's define t as this: x to the 1, x to the 1, the nth root of x. Then s be the nth root of a. Then x is equal to t to the nth power, and a is the s to the nth power. So the t to the n minus n can be factored out in this way, which can be written in this way by just divide both sides by t to the n minus sn and move this to the other side. You have this one. Then this can be written in this way, because t is x to the nth root of x, and s is the nth root of a, and t to the n is x, and a, s to the n is a. So this can be written in this way, which is this. Here now we replace this t as x, the nth root of x, and this s be the nth root of a, which makes this. Okay, then we think about the limit when x goes to a. Then, as you see, if x goes to a, then we have n times of x to the n minus 1 over n here, which can be written in this way. So So we now, the limit does exist, so we can say f of x is differentiable, and the derivative of x can be written in this way, which just fit with the power rule as you saw. Okay? And this example asks you to find the equation of a tangent line at this point. So all you have to do is just find the derivative of the function at that point, at this point. So that gives you the slope, then which is 1/3. Then the equation of the tangent line can be written as the slope 1/3 are here and point 1 and 1. So this equation can be written in this way. So that's the tangent line that passes through the point 1 and 1. Okay? So all you have to do is finding the derivative of the function to find the tangent line that passes through a certain point on the equation. Okay, now you know the constant multiple rule. It says the derivative of constant times the function when it's differentiable. It is the constant times the derivative of the function. Constant times the derivative of function. That's what it says. Some rule says the derivative of the sum of the differential function is equal to the sum of the derivative of each functions, like this. So, the sum rule. Okay, so that can be expanded in this way in general form. And here's another difference is that it works also for the not only for plus, it works for the minus. So it's a differentiation. It has a linear property. Expanded as a linearly. Okay, you can find the what? You can find the point of the curve where the tangent line is horizontal. What that means is the derivative is 0. So it is horizontal to the x-axis. So the point what you are looking for is the point where the derivative is 0. So just find the derivative and solve the equation. Then you have solutions like this. So you can find it. Those points are these two. These actually 3. So those are all the application of derivatives and the exponential functions for the derivative for finding the derivative. Let's find the rule for finding the derivatives for exponential functions. Okay, first, when f of x is equal to a to the x, when a is bigger than 0 and not 1, then from the definition we can have the simplified form like this. Then the f prime of x can be written in this way from the because those are the continuous function, you can replace the order of the limit, which gives us this, which is the limit, which is the first derivative of f at 0, which is like this. So even for the exponential function like this, you can find the derivative without much difficulties from the definitions. Okay, what this means is the rate of change of any exponential function is proportional to the function itself. You see, the derivative is the derivative of the exponential function is that same exponential function times some constant. Okay. So that's what this sentence says. Next, the definition of the number e. You are familiar with this number e. Okay, this exponential number e. Okay, this number e is very important constant, which is very close to this number 2.7182, etc. This number is also the limit of this function when n approaches infinity. Okay. Also, that E arises from in many different principles, and also that's the sum of the infinite series, which is this is dark here, but you will find. Okay. Anyway, this is a special case of this function, exponential function, when when a is equal to E and x is equal to 0, and it is this, and also the function is defined in this way. So E is a very special constant. Then let's think about the natural exponential function, e to the x, the derivatives of it. Okay, this e to the x, x is called the natural exponential function. Sometimes we just simply say the exponential function. When we say simply the exponential function, that means e to the x. Okay, that's the case, the special case of the general exponential function when a is equal to e. Okay, so functions like this. In this case, since f prime of 0 is equal to 1, so f prime of x is equal to e to the x itself. Actually, this is the very special. This is a very special. This is a very special property. The derivative of a function is itself. That's a very special property that we're going to use it a lot. In math department, a year ago, we had the invited speaker to talk 1 whole hour on this number e. So I have recorded the lecture here, so I will let you know the web address that I made, that you can go back to the lecture on E for 50 minutes. Okay, and yeah, you can do the examples with it. So now here is the product rule. So you asked me to show how to prove it. Okay, now you may take a look on this, the proof of the product rule, before we start. Now we prove the product rule. Product rule is like this. Suppose we have a composite function f of g, when f and g's are all differentiable, then derivative of f times g, f g is can be written as f prime g plus f g primes. This is what the theorem product rule says. Exactly. We can prove it from the definition of the derivative. Let capital F of x be the product of two functions f and g. Then f prime of x, can be written from the definition of the derivative in this way. Then from the definition of capital F, we can rewrite it in with the small f and g. Okay. From here, we subtract this term and add the same term here to make it same. Then we factor out f of x plus h and g of x to make it two terms like this. Then since those are all continuous functions, we can use the limit, the property or a property of limit on this equation to have this, which says limit of f of x plus h when h goes to 0, then this is just f of x like this. Then and this is just definition of g prime. So g prime of x is here, and this limit is just what? Just g of x, and this is the definition of f prime of x, which is this. So what makes us is the derivative of fg is equal to f prime times g plus f times g prime, which is the product rule that you have used a lot. We can use the product rule to do the differentiation of many functions. So for this case, for the derivative. So you just write the x to the 20th power here times the derivative of this one, which is 15 times e to the 15x, and e to the 15th times x times the derivative of x to the 20th, which is the 20 times x to the 19th. So this is what you have. So just it's so easy to use it. And next thing is a quotient rule. Quotient rule says this: the derivative of f over g is equal to f prime g minus f g prime over g square. Same thing. Let capital F as f over g and use the definition of the derivatives. Then add and subtract the terms in between to make it two different terms like this, which gives us exactly g of x, gx here, f prime here, f here, g prime here, over g square, which is the formula for the quotient rule. So the definition works very well. We can use the quotient rule to find the equation of the tangent line of this function at point 0, 2. All we have to do is find the derivative of this function y, and find then slope is then we know the slope at the given point is 1. So simply the equation comes from this, because the slope is 1 and it should pass the 0 and 2, which is 0 and 2. So minus 2 moves to here to make y is equal to x plus 2. It's just simple. And then trigonometric limits here. Yeah, you know, you should be familiar with this. And have you seen the proof of this formulas? Okay, since as you know, the derivative of this the function can be found from the definition like this, and by the similar process, yeah, we can find the derivative of the sine function is a cosine, and also the limit of the sine x over x can be found by the squeeze theorem, because this function is in between those two, and the limit of the left-hand side is 1, and also the right-hand side limit is 1. So the inside the limit should be equal to 1. That's how you got it. So squeeze theorem has been used to the equation, and the same approach can be found. Similarly, from the definition, you found the derivative of cosine x is equal to minus x, and the derivative of the tangent x can be found can be obtained with the quotient rule to have the secant square x. Okay, so suppose you have a function, then you can find the derivative. Now you can use all the rules. Okay, so these are the abbreviation of what you got. The derivative, the formulas for the trigonometric functions, as you know. I have uploaded the file of those formulas in a notice, so you can just download it and use it. So you don't have to memorize all this. When you need, you just you can produce it by using the definition. So you don't have to memorize all this. You produce it by yourself from the definition, or just use it from the table that you can easily find. Okay. Here now, since we can use the technology tools, now you can use copy here. No. Yeah, you can. Yes. So if you want to find the value, the graph of this has a horizontal tangent. What that means is we want to find the first derivative of this one and let it be 0 and solve it, which gives us the slope 0. Okay, find that point. Then that's the value that the graph has a horizontal tangent. So you find the derivative and solve it. So you now have the solution like this. Then you have the horizontal tangent line at each of these points, as you see here. Okay, here has the old edge of tangent. Also, that can be easily found if you can draw the graph of the function. With this, just copy this command and practice it in any of the Sage servers without logging in. So, and also you can directly find the derivative of it as well. But as you see, now if you can draw the graph, we can easily understand the nature of the functions. Here's the applications. Is there any question before we start the applications of derivatives? Okay. There are many. The application of derivative is so diverse. It can be applied in physics, chemistry, biology, economics, and other sciences. As I mentioned before, the derivatives has many different names in different disciplines. Okay, and this is another terminology. The average rate of change of y with respect to x can be written in this way: delta y over delta x. That means if delta changes this much, then how much of changes were made in y? That's what it is. It's an average rate of changes of y with respect to x. We keep those in mind. Here, this slope should be delta y over delta x, not delta x over delta y. Okay. Delta y over delta x. That's what the slope means. Okay, here. Okay, here. In physics, the derivative means the velocity. This velocity is an example of the derivatives. Okay, there are many examples. So they find the velocity. That means find the derivatives. That you can easily find it. Okay. And the next new terminology for you is the instantaneous rate of growth. This is also derivatives. The examples are made in here. For example, in this example, so consider the function like this. This is composite function. Then find the f prime of t and plot the graph of f of t together. Then draw f of x and f prime of f of t and f prime of t together. Then you will see the blue ones are the original equations, and the red ones are, because here, tangent. The plot P1, the P1 is the original equation, t times 1 minus t times e to the minus t over t, from minus 2 to 3. Here. So blue is here. Then find the derivative of it, which is f1, which is differential of f, which is f1. So this f1 is red. And then the third one is a tangent line at t is equal to minus 1, which is green here. So we have a function here. We have a function of the graph of the derivative here. We have a tangent line at x is equal to 1 here with the green equation. This all can be made with this command, so you can practice. In here, the derivative of f can be found in this way. If you just give a command that what is f1, then it gives us this value, which is the derivative of this one. How did you get it? This is a product of three functions. So you use the general form of the product rule. Okay? Okay, here's the exercises and that you may practice. Here, we may start with the simple example, the finding the derivatives of the polynomial, the linear combination of the continuous functions, and find the derivative of functions, and find the tangent line, and draw the tangent line at a certain point, and some application point problems are there. And you draw the graph and find the limit of the certain functions, and web browsers, for example, find the limit of the certain ones, then you may evaluate it to get this. If you change it, then you can find the limit of such a functions. It must be a very big number now. Okay, anyway, yeah, you can make all the changes to do so. So you can solve those by your hand by changing the numbers and functions or exact problems. But also you can use the Sage or other computational tool to deal with such problems. So I will not ask you to compute these simple problems by hand in the examination. So you do not I want you to find the solution in your own ways for any type of the function that I can put in the examinations. Okay, anyway, so there are some problems that you already started to solve in Q&A. Okay. What else? Let me explain just one example here, the problem 23. If a stone thrown vertically upward the velocity 10 meters per second, then its height after t seconds is this. Then what is the maximum height reached by the stone? How you can find it? How? Maximum height. That's the point that when velocity is 0. Okay? So what's the velocity? So first derivative. Find it. And solve it is after let it be 0. Okay? Then solve the equation to find when the velocity is 0. That's just solving the finding the first derivatives. So that gives you the solution. What is the velocity of a stone when it is 5 meters above the ground on its way up? Yeah. So let's set it set it up the equation that the height is equal to 5 and solve the equations. That's all you have to do. So such problems are the problems that you already have dealt with a lot before you come into the university, particularly the 성균관대 University. You must know all these. Only differences are the problems are written in English, and it's a little simpler than what you have seen in college entrance examinations. Okay, this is what actually I showed you before, but here I made it as one example. Okay, any questions for the section 3.2?